Hello, eighth graders. So we are now talking about relative age dating in rocks. We've already covered absolute age dating, so where we use carbon 13, 14 atoms in order to identify an actual age. Now we're going to focus in on what truly you need to know and all that fun jazz. Let's get into it. So we have middle school Earth Science Standard 1-4 and middle school Life Science Standard 4-1. This is where that Life Science Standard really starts to come into play. So 1-4 states that you'll construct a scientific explanation based on evidence from rock strata for how the geologic timescale is used to organize Earth's 4.6 billion year old history. And then the life science standard that we'll hit more so today is 4-1, which states that you will analyze and interpret data for patterns in the fossil record that document the existence, diversity, extinction, and change of life forms throughout the history of life on Earth under the assumption that the natural laws operate today as they did in the past. This is the example of in the past. Even if you were to jump up into the air like you would now, you still come down to the surface. You don't just start floating off into space. And that's because we can assume that gravity worked the same way then as it does now. Same with every other sort of construct of time in life. Okay, what you really care about is what you are going to be able to do. So you will be able to utilize the principles of geology to accurately age rock strata. You'll be able to infer the use of relative age dating to estimate the age of rocks by using the index fossils in dating the fossil record. So this is where that life science standard comes into play. This is the concept of being able to look at fossilized record and identify how old something may be just because of where it's located within our surface. So we'll go through all of that. So make sure that you have your notes in front of you, for sure the whole group notes, and we will go through all this. So relative ages of rocks. So the age of rocks that geologic features compare with other rocks and features nearby. So it's saying like, oh, that one looks like it may be older than that one because of where it is in its position. This is the idea of being able to say, I'm older than my brother but younger than my sister, without giving for sure like how much older or how much younger. So it's just giving you that birth order rather than giving you the actual age like we discussed with absolute age dating. So we can do the same thing with rocks and fossils we can give you essentially a birth order, but not a for sure date, just because that takes a lot of time and energy in math, and we don't do math in science. Well, I don't do math in science because that's just not how I operate. But so that is relative age dating. It's just giving you an idea of what order things may go in. Now, this is all contingent on whether humans are involved or not. So let's talk about some of those principles. So we have three major principles of relative age dating that we really need to focus on. So we have to look at superposition, original horizontality, and lateral continuity. So I'm going to explain and I'm going to show you diagrams. Okay, so the principle of superposition. This is the principle that in an undisturbed rock layer, so humans haven't touched it, we haven't dug it out, nothing like that, the oldest rock is always going to be on the bottom. When we talked about deposition of sediments with sedimentary rocks, it always has to start on the bottom. So your oldest stuff gets placed here. Then you get more deposited on top, and then on top, and then on top, and then on top, until you have your most youngest rock at that very surface. That is what we can assume our rock layers look like as we go into the earth, as long as we don't disturb anything. Okay, so what I mean by that is like we built this house over a year ago now. We had to disturb the rock layers because we had to dig out our basement. So as soon as you dig out, you just throw it into a pile, and now your ordering gets all goofy. That is what I mean by disturbing the rock layers. Okay, because then when we backfill it back into where it needs to be, it's not going back in oldest to youngest, it's just being thrown in. Okay, so that's the law of superposition. The principle of original horizontality. Okay, this is the idea that most rock formation materials are deposited in horizontal layers. So remember, horizon is like that line that you see going out. Okay, so they are deposited in horizontal layers. Sometimes the layers may be deformed or disturbed due to natural causes. We'll talk about those in a moment. But even though they might be deformed or disturbed due to natural causes, we can assume that the layer that goes across is relatively the same age. This example is like with the Grand Canyon. We can assume that at the very bottom of the canyon, we can see, if we could make a cross section, we could see the oldest rock at the bottom. But even though we have this space where there's nothing, there's just atmosphere, we can assume that if we go from this side all the way over to this side at roughly the same space, those two rock layers, even though they're spread apart, are relatively the same age. And it goes up and up and up, all that fun jazz. Okay, so that's the principle of original horizontality. Everything goes horizontally. Okay, now lateral continuity. Lateral continuity is that continuous sheets in all lateral directions. Sheets or layers continue until they thin out or meet a barrier. So what this means is as things progress out, even if you come up to some sort of a structure, whether it's mountains or a forest sometimes, or the fact that you run into the ocean along the coastlines, that as long as it is the same continuous sort of thing, even though it dissipates out, that is again relatively the same age. This next slide has diagrams to hopefully explain it a little bit better. So the law of superposition. So that is this one here. The law of superposition, where we have the oldest on the bottom and the youngest on top, because the way things have to go is like that. The couple great examples would be like if you were to think of your laundry basket. Now in our house, I do laundry typically on Saturdays or Sundays. So if I do laundry this coming Saturday, that means that Saturday's clothes will go into the empty laundry basket. And then Sunday's clothes will go on top of that, Monday's clothes on top of that, Tuesday, Wednesday, Thursday, Friday, all the way to Saturday again, where I have to do laundry again. Okay, your oldest clothes, the clothes that you wore the longest time ago, should be at the bottom, as long as you don't disturb it. If you're like, gee, what is this whole laundry basket concept? If you imagine the pile of clothes on your floor, the oldest is on the bottom and the most recent worn outfit is on top. Okay, that's the law of superposition. Yeah, so that. The law of original horizontality. So this is even though there might be a bump here, or like we said with the idea of the Grand Canyon, things like that, everything is still going to be relatively the same age, no matter whether this bump was here or not. So if I were to be able to flatten that down, it would still go oldest all the way up to youngest. Okay, and then finally, the law of lateral continuity. So this is where even though you get these gaps, even though if this were to be a coastline and it dissipates or starts to like dwindle, it is still the same age across that way. So even if you were to then meet up at the other coastline, that should be relatively the same age. Okay, so those are the first three. We have two more we have to talk about. Okay, so we have inclusion and cross-cutting relationships. So the principle of inclusion is that a piece of an older rock becomes a part of a new rock, or sediments or magma become a part of the new layer. So what does this mean? This means that if you look at this diagram over here, you still have oldest all the way up to the youngest. But if you get a magma chamber, that starts to cut through, or in this case, it is a magma dike, things like that. This now kind of absorbs everything it went through. So all the stuff that it went through now is melted down into that new rock. So that is inclusion. That plays a part with this cross-cutting relationships. And that's if one geologic feature cuts across another feature, that feature that it cuts across is older. So what does that mean? That means one still had to be deposited before 4. Okay, 2 had to be deposited before 4 because since 4 goes across it, it has to be newer because these first 3 had to be there in place in order for 4 to cut across. But then 4 stops and now 5 is laid on top. So again, 5 would have to be the youngest because 4 did not continue. 5 was the last thing to be deposited. Okay, that is cross-cutting relationships. That something that cuts across another has to be younger than what it cut across. Okay, we are going to practice these during the independent portions. Let's talk about unconformities. So this is where we get those random sort of experiences where rock gets all twisted or pushed or divided or whatever, because that's how geoscience processes work. So these are all of those instances. So there are 3 different types of unconformities. And essentially what an unconformity is a surface where rock has eroded away, produced a break, or a gap within our rock record, because nothing in this world is perfect. Okay, so there are 3 different types. We have a disconformity, we have an angular unconformity, and we have a non-conformity. So the disconformity is younger sediment layers are deposited on top of older. Horizontal sedimentary rocks have been eroded away. So this is where you get, like, if all of a sudden the Grand Canyon were to start being filled in with sand, this would be a disconformity because going across the original rock bed would be the relative same age, but then you get these random new sediments that are placed within that are much, much younger. Okay, that is a disconformity. An angular unconformity. This is where sedimentary layers are deposited on top of a tilted or folded sediment layer that has been eroded. So when we get those convergent boundaries where you start getting mountain building especially, so these start going at an angle, but let's say that that angle stays there, but now you have layers going on top and then covering that up. That is an angular unconformity. Angular, it's at an angle, isn't it straight up and down? Unconformity, you get that younger rock. Okay? And then you have nonconformities, because why not make things just that much more weird? So an unconformity is where younger sedimentary layers are deposited on older igneous or metamorphic rock. And then some of these igneous or metamorphic rock get eroded away. So if you have an old volcano, okay, it has since gone dormant, if not extinct, and then sediments start filling in on top of it. Kind of sort of what has started happening with Hawaii, okay, where you get just all of this. The nonconformity portion of it comes in the fact that we're not just dealing with sedimentary rock layers, we're now dealing with metamorphic and igneous. That's the only difference. But again, my next slide has diagrams that I feel like explain it a little bit better. Okay, so our disconformity. Remember, this is if the Grand Canyon were to be filled in with sand. So you have these rock layers right here and below that were placed and they were perfect. Okay, but then this portion started to be eroded away. Wind, water, whatever. So then all this new sediment is starting to fill it in and starts filling in that space where technically if you were to go across, it's supposed to be relatively the same age, which would be older. But you get this new rock filling it in, that's a disconformity. Okay, so you got to look all the way around it before you're like, yep, nope, wrong. Okay. Angular unconformities, you have all these sedimentary rock layers that because of geoscience processes, convergence zones especially, are now at a weird angle, and now everything is getting filled in around it or on it to where it starts going more horizontally again. That is your angular unconformity. And then finally, this is an old volcano. It has since extinct, went dormant, whatever. It's no longer producing magma. So it's just kind of there. And now these sediments are filling in around it to cover it up. That is your nonconformity. Okay? Hopefully that all makes more sense now. Or is it clear as mud? This is where you will be able to work independently. If you need anything, just remember your champ's expectations and let me know. Okay, if you're continuing with PowerPoint, sweet, let's keep going. So we're going to test ourselves. So understanding the difference in your principles and all that kind of stuff, what I want you to do is I want you to order the layers from oldest to youngest. Okay, remembering the principle of superposition, remembering the principles of cross-cutting relationships and original horizontality, all that kind of fun jazz. What I want you to do is pause me for a moment, okay? Write out your numbers from oldest to youngest, and then unpause me for the answers, okay? Okay, hopefully you're unpaused now. You actually paused me. If not, you just saw me sit here and do weird things. Sweet. Okay, so let's start with the oldest. I always like starting with the oldest because with the law of, or the principle of superposition, oldest should always be at the bottom, okay? But in this case, we have some really cool sort of things. So what has happened is we have an angular unconformity, we have a nonconformity, and then cross-cutting relationships, all that kind of fun jazz. So what I like to do is I like to imagine that this, that is all at an angle, if you were to imagine it tilted to where it is right side up, which one would be at the very bottom? Well, if I were to look, okay, you have 5 here, 2 cuts across 5, so 2 has to be younger than 5. And 3 cuts across 2, which means that 3 has to be younger than 2 and younger than 5. So I already know it needs to be 5, 2, 3 at least. Okay, but I'm going to keep looking at 5. Okay, so I see this like weird brick-like texture that is here. Ooh, it's at a weird angle up here. I have this orange speckly things. There's some there. Then I have the yellow. Okay, yellow is number 4. So that is technically below 5. So your oldest layer is layer 4. Okay, hopefully you're with me still so far. Okay, then I'm going to go back up and I'm like, okay, well now I know it goes 4 and then 5 because 5 is sitting on top of 4. And then 2 went across 5. but 3 went across 2. So that means that your order should be so far from oldest to youngest, 4, 5, 2. Okay? Now, looking at 3, yes, it cuts across, so it's younger. Okay? But it also cuts across 6 and 1. So, again, law of superposition, 6 should be older than 1 because it is below it. And then you have 1, and then 3 is the youngest of them all. Okay, so your order from oldest to youngest should be 4, 5, 2, 6, 1, 3. Okay, good. If you're super confused right now, please pause this, come chat with me, okay? Let's test ourselves again. Now I want you to order the layers from youngest to oldest. Okay, now take a moment. If you want to start from oldest, so bottom, and work your way up, perfect. If you feel super duper confident in yourself and you can go youngest to oldest, fantastic. But pause me now, write it out. There's no penalty for getting it wrong right away. Okay, so pause and then come back to me. Did you pause? Okay, so again, like I said, I like working from the bottom up because that's just how my brain works. So I'm going to take a peek here. We have cross-cutting relationships. We actually have a fault line going through. We have some weird sort of disconformities, all that kind of fun jazz. So I'm going to look. Okay, so trying to start toward the bottom. So I see C is at the very bottom and D cuts across it. So that means that C still has to be younger or older. Sorry, C has to be older than D. Okay, I'm going to keep kind of working my way up. Okay, then I have B. Again, D is cutting across B. So B had to be there first. So that means oldest is C, then second is B. Awesome. Still following D. Wow, there's this weird fault, and that kind of throws things off. But I see that D continues over here. It's cutting across A. So then A had to be there before D was. Then D, because D had formed, and then E's fault occurred. So from youngest to oldest, working our way down, we have E, D, A, B, C. Okay? Again, if you're super confused, come talk to me. Let's talk about it. Okay? One more practice. I promise you, it's worth it. Order the layers from youngest to oldest. Okay? You have nonconformities. You have cross-cutting relationships. You have angular unconformities. All that kind of fun stuff. So this one, there's a lot of letters to kind of juggle. So work whichever direction works best for you. Excuse me. And then list them from youngest to oldest. Okay? Make sure you pause, please. Okay. So let's go over this. Depending on how you want to look at things, it could kind of sort of go in a little bit of different ways. So we could go with the nonconformity of B was there and then D and all that kind of started forming after it, but that doesn't necessarily fit the hypothesis without seeing the rest of where B is. So to me, D would have to be the oldest. Again, I take that picture and I imagine it just twisted a little bit to where it's all going horizontally. So D would be at the bottom. I imagine it as B cut across all of those layers. So oldest, D, then J, I, A. Now we have this weird, you have G, but you have F cutting across it. So G had to be there first. Then we have B, which had to have been there before F cut across it. So oldest, D, J, I, A, G, B. Okay, now F cuts across all of this. So E had to be there before, so it goes from B to E, then C, and I see that F stops right here. So then F with A, H, not A, H, finishing out on top. So from youngest to oldest, we have H, F, C, E, B, G, A, I, J, D. How'd you do? Hopefully this is coming a little bit easier now. Okay? Now, correlations. So correlations is essentially trying to find things that match up to explain why things are kind of the way that they are. So this is matching rocks and fossils from separate locations or making those connections. The type of fossils that we use are called index fossils. Now, index fossils are very special. Love index fossils. These are fossils that represent a species that existed on Earth, but they only existed on Earth for a very short amount of time, but there was a lot of them at that time. And they inhabited more than just one location. So these are organisms that basically just had this like baby boom over a short period of time. And they were able to migrate, or they had multiple of these species all around the world at this point in time. Now, they aren't always helpful in determining relative age of rocks and layers, but at least you can say, okay, this index fossil happens here. So anything that you find below that, okay, no matter how far below, has to be older. But anything found above it has to be younger. Again, not giving you a date or age, or at that point in time, you might not even know how many years, like how many years before that actual organism went extinct. Okay, so let's talk about what makes a good index fossil, because not every fossil can be an index fossil. So next slide. An index fossil has 4 requirements it must meet in order to be a good index fossil. So, first of all, it must be widespread, meaning that you're finding this fossil in more than just 1 or 2 locations. And they should be in locations that are fairly spread apart. So we're looking at, like, if we're looking in North America, we should also be looking in Asia, and we should also be looking in South America, like that sort of a distance, not like the difference between like here, Moorhead, and Dilworth. It needs to be over a greater span. So they need to be widespread, found very different places, spread out horizontally, okay? Short-lived. They can only be found in a very narrow range of geologic time. Now, narrow range is a relevant term. Narrow age for us would be like, oh, 1 to 2 years, or if we're even talking, it needs to be in the last like week or so. When we're talking over geologic time, we're talking they can only have existed for a couple thousand years, maybe a couple hundred years. That's what we're talking about. Remember, if we're looking at 4.6 billion years of history. So they need to be short-lived, meaning that we're not going to find it like certain bacteriums would not be great, because bacteria were the very first organisms really to get going, and we still have them today. So they're very long-lived. Versus short-lived, we have things like trilobites, ammonites, things like that, that really were only there for a very short period of time on Earth. So again, spread out horizontally, not vertically. Okay, easily recognizable. this is where they have to have a large amount of population, and they need to be able to be like, oh, that's this sort of a thing. So again, going back to those bacterium look very, very similar. They're these like pill-shaped sort of things, to where without really looking at their DNA, you may not know exactly which bacterium they are. So it needs to be able to be like, oh, that is this. So that we can sometimes use dinosaur fossils as index fossils just because they were only around for a couple thousand years. And they went extinct, to where we know everything above where we find dinosaurs is less than 65 million years old. So yeah, finally, well preserved. We talked about this in your formation of fossils notes, that certain things just don't preserve as well. So we're looking for things like bones and shells, because they actually preserve and you can get a better picture of what is all there or what should be there and all that kind of fun stuff. So again, this is where the trilobite, that is like the horseshoe crab, or the ammonite, which looks like a snail shell sort of a thing, those work perfectly because they have an exoskeleton, or they are made out of calcium because they're a shell, things like that. So they are able to be preserved rather than like a leaf of a plant that was only around for a certain amount of time, because there may not be many leaf fossils left behind because they don't preserve nearly as well. Not saying that we don't use plant matter as possible fossils, but yeah. So in order to be a good index fossil, they have to be widespread, short-lived, easily recognizable, and well preserved. Okay, so let's put those ideas to the test. More practice. So I want you to look at these, and I want you to figure out what is something that is short-lived, widespread, well-preserved, and easily recognizable. Okay, so the way that I like to do this is I like to start typically at the smallest outcrop, and just kind of look at the different fossils that potentially could be used. So if I look here, I have this little V-shaped thing. Okay, so I'm looking for this V-shaped thing in my other two outcrops. Now an outcrop is just a vertical taking of a rock layer or rock layers. So we have 3 different outcrops we are working with. Okay, so this little V thing. So I'm going to look in outcrop 2, and I'm just going to kind of follow it down, and oh, I don't find one. I do have one over here in outcrop 3, but I don't have one in outcrop 2, so may not be the best choice. Okay, let's keep looking. Now I have this weird little like half crescent moon thing, and I'm going to be 100% honest. As I'm recording this, I can't see what's below P. I don't know what's in layer Q. I don't remember what's in layer Q. I think I know what's in Q, but that's just where we're at. Okay, so that I don't see any other one in either of the outcrops. So D, really not a good plan to use. Okay, so then we go over here and we got this weird little algae thing. I don't see anything in outcrop 2. And again, I think I know it's in Q off the top of my head, but yeah. So again, not our best choice. So that leaves us up here with outcrop 1, and we have this shell crabby looking thing. Awesome. I'm going to go to outcrop 2, go down. That's an eel. That's a weird taco thing. That's a claw. Oh, I have one here. Okay, now let's look in outcrop 3. That's what I'm pretty sure is back here behind Q. Hopefully I circled it. Right now it's just going across my face. So that That is widespread. I found it in not just outcrop 1, but 2 and 3. Okay, it doesn't go vertically, meaning that I don't have it here and here, or here and here. It's just in the one layer in either outcrops. Okay, it is easily recognizable. I can see that that is a trilobite. I can see that it is a trilobite. I can see that it's a trilobite, meaning that I can easily see it, identify it. Okay, and it's well preserved. Obviously, in a picture, you're not going to be able to tell, but we can assume that it was well preserved because it's there. Okay, so if I were to ask you which would be used as the index fossil between these three outcrops, you would say the fossil found in layer A, K, and Q. Okay, awesome. Let's do one more practice. So which is the index fossil? Okay, look, kind of go through. Remember, widespread, found in many locations, easily recognizable, short-lived is this middle one, by the way, and well preserved. Okay, so pause if you need to. Come back in a moment. Okay, so let's look at this. Outcrop 1. Okay, I have this weird little like bug-looking thing. Ooh, but right above it, I have it again, which means it was not short-lived. It lived for a long time. So I'm just going to make sure that that is nose goes. Okay, awesome. Moving on. Now I have this taco looking thing. Okay, gonna look in outcrop 2. I have a taco thing. Ooh, but I have a taco thing here in those ones. So again, not a great option. I don't want to use something because it is not short-lived. Okay, and then finally we have this shell, and I have a shell here and it's not going vertically, a shell here, again not going vertically, and the shell here. So which fossil should we use as the index fossil to assume relative age? Everything below it is older, everything above it is younger. We would use the shell as our index fossil. Okay, we are going to get a lot more practice with this in the next couple days. We have activities at the wazoo for you to work on. If you have any questions, please come and chat with me. Make sure you complete the exit slip that goes along with today's notes. I believe the one for today is the principles of relative age dating one. Don't quote me on that in this. It'll be correct in the Schoology page. Awesome. Again, any questions, give me a holler. I want to answer them and help you with this because this is what a majority of your test is going to be made up of, is relative age dating. So, awesome. Thank you for bearing with me in all the practice. If you need anything, let me know. Thank you.